Hello everyone. Now we are going to start our new chapter, that is bending stresses in beams. In previous lectures we have studied about the stresses. We know that what is stress, and we know what is beam. That also we have studied in previously. Now we are going to study about the bending stress. So first of all, we have to understand what is bending stress. We have understand just only a tensile stresses and compressive stresses. Now we are going to study about the bending stress. Means whenever our beam is going to deflect or bend, at that time the stresses are developed in particular cross section of the beam. That stresses we are going to study now. So what is exactly bending stress? Now let's start to understand pure bending stresses. We are going to just consider only bending. There will be a shear also, but just now we are going to understand only a bending. So what is bending stress? When a beam length is subjected to a constant amount of bending moment and zero shear force, the stress is up to across the cross section of the beam due to bending is known as pure bending stress. So just we are neglecting the shear force over here. We are only considering bending. That's why it's called pure bending stress. Now, here assumptions in the theory of pure bending, we are going to derive the equation for the bending stresses in beams. So, for that, some of the assumptions are there. This kind of assumptions is present there, then and then the equation is utilized for the bending stresses. So, which are the assumptions are there? First one is the material of the beam is perfectly homogeneous and isotropic. Here we are talking about the beam. So, in that beam, the material that used in the beam is homogeneous and isotropic, means throughout the length the same material are there, and throughout the length the properties of that materials are same. The beam is straight within its elastic limit and Hooke's law is valid. We know that what is elasticity. So, up to that elasticity, we can allow that bending as well as Hooke's law that we have studied, that Hooke's law is also valid for these bending stresses. The transverse section which were plane before bending remain plane after bending, means the section of our beam having dimension B and D before bending and after bending, that cross sectional dimension B and D doesn't change. Fourth one, each layer of the beam free to expand and contract independently, means whenever our beam is going to deflect, there are developing two layer, compression as well as tension, both are there. So they both layer are expand and contract independently. There will be no restriction for the expansion and contraction of that layers. Now, the value of Young's modulus is the same in tension and compression. As we know, the material is isotropic, so the modulus of elasticity as well as all other properties are same for the section. So, the modulus of elasticity for the tension and compression are always same, that we know. Now, the theory of pure bending. Here, our length of beam, whenever it will be deflect, it creates something bending like this. So, the top portion from the neutral axis is contract and bottom portion is in tension. So, we are going to just considering a small part of this beam, that is called dx. Due to bending, the top layer will be a AC become AC dash, A dash, C dash. As we propose toward the lower layer of the beam, they call suffered the compression, but a lesser degree until they come across the RS. Means it is a neutral axis, so there will be no change. The neutral layer and the neutral axis, what it means? Due to bending of beam, all the layers of above RS layer are the compressed and the below RS layer is a stretch, means it is in a tension. But the layer RS which will be neither compressed or nor stretch, it is in a neutral axis or neutral layer. That axis is called a neutral axis. The line of intersection of the neutral layer which any normal cross section of the beam known as the neutral axis of that section. If the section of the beam is subjected to pure sagging bending moment, the stresses above neutral axis are compressive and stresses below neutral axis are tensile. The neutral axis and A, there is no stress any kind of, that we know. Here, this is our cross section of the beam, this is our neutral axis, and from the below of this it is coming in a tension, and this one top portion is in compression. So, it is compressive stress up to here, and here it is a tensile stress that we have to finalize for the beam. Now, the most important thing, that is moment of resistance. What it means? We know that whenever the load apply on the beam, due to that load our member will be bent, that we know. But whenever we are going to see all the buildings, if have you ever observed that any beam of the building which deflect? No, बिकॉज हम जब भी कोई भी बिल्डिंग्स देखते हैं तो वो बिल्डिंग में सारे बीम जो है उस पर लोड लगते हैं। लोड लगने की वजह से वो बीम बेंड होने चाहिए, बट हमको कभी भी वो बीम बेंड नहीं दिखते हैं, बिकॉज whenever the load applied on that beam, but our support of that beam, which is column is going to develop resisting moment in that beam. So, it will be balanced the our section, and that resisting moment is developed by the support as well as by the material that we are using in the beam. That resisting moment is called moment of resistance. So, how much moment of resistance is developed? That जितनी भी हमारी मोमेंट आ रही है उतना ही मोमेंट ऑफ रेजिस्टेंस जनरेट होगा, तब जाके हमारा बीम स्टेबल होगा, राइट। तो ये जो है मोमेंट, ये मोमेंट ऑफ रेजिस्टेंस वो उतना ही डेवलप होगा जितनी उस पर मैक्सिमम मोमेंट आने वाली है, राइट। तो ये मोमेंट ऑफ रेजिस्टेंस जो है वो कहाँ से डेवलप होगा, जो मटेरियल हमने यूज़ किया हुआ है बीम में, कंक्रीट एज वेल एज रेनफोर्समेंट, वो दोनों ये मोमेंट ऑफ रेजिस्टेंस डेवलप करते हैं विद द हेल्प ऑफ सपोर्ट, राइट। सो व्हेन a beam length is subjected to constant amount of bending moment on one side of neutral axis, there are compressive stresses, and on the other tensile stresses are there. These stresses form a couple of moment must be equal to the moment. The moment of this couple which resist external bending moment is known as moment of resistance. Now, equation of the bending stress that we have to finding out. So, in that case, we are going to just consider a small length of our beam, that is delta L, right. So, PQ minus PQ, P dash Q dash. So, strain is equal to delta L upon L. So, this is our delta L divided by original length, right. So, this is our cross section and having PQ length, right. This is our P dash Q dash, this is the PQ, right. So, we know that delta L is equal to PQ minus P dash Q dash. So, that much length is reduced. Now, epsilon is equal to delta L upon L. So, original length of this member, that is delta L, or else it's PQ. Now, we are going to just understand that geometry of the figure of this P dash Q dash upon R dash S dash is equal to R minus Y upon R. मीन्स ये वाला जो हमारा पोर्शन हमने कंसिडर किया हुआ है, ये डिवाइडेड बाय ये न्यूट्रल एक्सिस इज इक्वल टू यहाँ तक कि उसकी लेंथ कितनी है, तो आर माइनस वाई, यहाँ तक आर माइनस वाई। सो पी डैश क्यू डैश जो है उसकी लेंथ मीन्स रेडियस आर माइनस वाई है, और आर डैश एस डैश की रेडियस जो है वो है आर। नाउ फ्रॉम दिस इक्वेशन वी कैन कंसिडर दस 1 माइनस of both side. So, r dash s dash minus p dash q dash upon r dash s dash is equal to r minus r plus y upon r. So, it is just remove these two r. So, it is y upon r, right. Now, our equation, that is pq minus p dash q dash upon pq. So, it is called epsilon, means delta L upon L, and epsilon is equal to stress upon Young's modulus. So, it is a F upon Y is equal to E upon R. Now, just consider this cross section. Our equation, that is F is equal to Y into E upon R. Now, the area of this small part, that is delta A, the total force of the layer, that is F into delta A, stress into area, right. It's called force. So, it's a y into E upon R into delta A. So from this equation we can get the m upon I is equal to E upon R. So our final equation of bending stress, that is m upon I is equal to F upon Y is equal to E upon R. This is our generalized equation for the bending stresses in beams. Now from this we can calculate all the stresses developed in beam as well as moment of resistance of particular beam. But for that we have to memorize this maximum bending moment that developed in beam due to load and type of beam and type of load, that we have to memorize that moment. For the simply supported beam with centrally point load, the equation is WL by 4. This is the maximum bending moment. Whenever the simply supported beam over there and the eccentric load W at A and B distance, so the maximum bending moment, that is WAB by L. This we have to memorize. Third one, simply supported beam with UDL, W kilonewton per meter. So equation for that, WL square by 8, that we have to remember this. Cantilever beam with point load at the free end. So it's create maximum moment in the beam, that is W into L. Cantilever with UDL. So maximum bending moment it's generating for that beam, that is WL square by 2. So these are the 5 cases we have to memorize. Simply supported with central point load, that is WL by 4. Simply supported with eccentric point load, that WAB by L. Simply supported with UDL, that WL square by 8. Cantilever with point load at free end, it's WL. And cantilever with UDL, it's WL square by 2. That we have to remember these 5 cases. Now this is the flitched beam, but this is not in your syllabus, so you have to just skip this, but it's important, that's why I am just give you an overview of that particular flitch beam. Whenever we are going to use different materials in a particular beam, so what exactly happening, that we have to understand for the cases. When a section of the beam is made up of 2 or more different material and joined together in such a manner that it's behave like a single piece and each material bends to the some radius of the curvature, such beam is called flitch beam. In old type of home you have seen, that is in villages, they were used previously wooden plank with steel plate on that. देखा है कभी आपने? पुराने जो हाउसेस होते थे हमारे, उसमें हम वुडन का बीम यूज़ करते थे और उसको स्ट्रेंथन करने के लिए टॉप एंड बॉटम में हम स्टील की प्लेट लगाते थे। तो वो हो गया फ्लिच बीम। तो वो फ्लिच बीम हमें कैसे स्ट्रेंथ देता है, वो कैलकुलेशन इसमें दिया हुआ है, बट ये आपके सिलेबस में फ़िलहाल नहीं है, राइट? तो ये आपको स्किप करना है, बट ये जस्ट मैंने आपको आइडिया दिया कि अगर 2 डिफरेंट मटेरियल है, ये 2 वुडन प्लैंक्स है, उसमें स्टील प्लेट रखा हुआ है और इन तीनों को ऐसे मर्ज किया है कि इट्स बिहेव लाइक अ सिंगल पीस, तो उसके इक्वेशंस जो है वो थोड़े बहुत डिफरेंट हैं। F1 इज इक्वल टू E1 upon E2 into F2. Means F1 upon F2 is equal to E1 upon E2. That also we can say that, right? यानी मटेरियल के जो स्ट्रेसेस हैं और मटेरियल की मॉड्यूलस ऑफ इलास्टिसिटी, उन दोनों का रेशियो जो है वो सेम हम कंसिडर करके उसको कैलकुलेट करते हैं, राइट? ये भी दो अलग अलग मटेरियल है, राइट? तो उसको भी हम कैसे कैलकुलेट करते हैं? अगर ये हमारा स्टील है तो स्टील की जगह अगर हम वुडन यूज़ करना चाहते हैं तो इसकी जगह उसकी लेंथ इतनी आएगी, तो वो कितनी बढ़ जाएगी? बी डैश अपॉन बी डैश इज इक्वल टू एम बी जितनी, यानी एम जो है दैट इज मॉड्यूलर रेशियो, मीन्स इट्स ए रेशियो ऑफ मॉड्यूलस ऑफ इलास्टिसिटी। सो ये इक्वेशन से हम उसको फाइंड आउट कर सकते हैं कि अगर हमें स्पेस कम मिल रहा है तो हमें वुड की जगह स्टील यूज़ करना है और स्टील की जगह वुड यूज़ करना है, तो हम कैसे मटेरियल को रिप्लेस कर सकते हैं फॉर दैट पर्टिकुलर केस। ओके, सो थैंक यू वेरी मच। ये पर्टिकुलर केस में आपको सारे इक्वेशंस याद रखने हैं, राइट, जो हमने अभी फाइनलाइज किए। थैंक यू।